The normal or Gaussian distribution. A continuous random variable x is said to follow a normal distribution with the mean, mu, and standard deviation of sigma, as denoted by this symbol, if the probability density function or PDF of x is defined by this equation, where exp stands for e raised to, where e is equal to 2.718, blah blah blah, and pi is equal to 3.1415, and so on. So in this case, we have exp, meaning to say e raised to this one here, the expression here, and then x is the value of the random variable, mu is the average, and then this sigma is the standard deviation. So this is the pi, and then another sigma here. A normal or Gaussian distribution is a continuous probability distribution that is symmetric about the mean. So when we say symmetric about the mean is in the middle, and then the right side of the mean is equal to the left side of that mean. It is also called Gaussian distribution in honor of the renowned German mathematician Johann Carl Friedrich Gauss, who derived the equation of its probability density function. So he derived this equation. It is the most common and important probability distribution. One of the main reasons for that is the central limit theorem. This theorem states that both the sum and the mean of many random variables defined by real-life quantities have approximately normal distribution. Thus, in studying such random variables, statisticians often make the assumption that they are normally distributed. The graph of the probability density function of normal distribution is a bell-shaped curve known as the normal curve. So this is the normal curve. The normal curve has the following characteristics. Number one, the graph is symmetric about a vertical line. So this is the vertical line, the middle, through the center of the curve where the mean, mu, as well as the median, the mode are located. So this is the mean. In normal distribution, the mean, the median, and the mode are the same. And this is symmetric. This side, right side, is equal to the left side. The total, number two, the total area of the region that lies under the curve and above the horizontal axis is equal to 1. So the whole thing below the normal curve and then above the x-axis or the horizontal line, the shaded part is equal to 1. Why is that so? Because we're talking about probabilities here. Okay. Number 3, the tails of the normal curve are asymptotic. So when we say asymptotic, this tail is actually going to the horizontal line, the x-axis, but not touching it. Not touching the horizontal line. So that's what we call asymptotic. Next, the empirical rule for any normally distributed random variable is, number 1, approximately 68.26 of all the values of x lie within one standard deviation. So this is one standard deviation from the mean. So this is one standard deviation from the mean above, and then this is one standard deviation from the mean below. Adding the area below that is 34.13 times 2. That is 68.26%. So again, approximately 68.26% of all the values lie one standard deviation from the mean. And of course, from 13.59 up to 13.59, adding all the areas, we have 95.44% of all the values lie within 2 standard deviation from the mean. So 2 standard deviation from the mean. Lastly, 99.74, so from this 2.14 up to 2.14 here, of all observations or data lie within 3 standard deviation. So 3 standard deviations from the mean. So that's mu plus 3 or mu plus 3 sigma. Mu minus 3 sigma. So the whole thing is equal to 99.74%. Let's have this one. A normal distributed random variable x has a mean of 500 and a standard deviation of 40. Determine the range of values of x that lies within 1 standard deviation from the mean. Okay, so let's plot this mean 500 in the middle, 500, and then standard deviation of 40, and then we have 1 standard deviation from the mean. 1 standard deviation from the mean, so that's 500 plus 1 times 40, and then 500 minus 1 times 40. So the whole thing is 1 standard deviation from the mean. The range is between 500 minus 40, which is 460, so this is 460 here, and 500 plus 40, which is 540, this one is 540. So the range is between 460 and 540, and about 68.26% of all the values lie within this range. Next, the lowest value. Determine the lowest value of x that lies at least 2 standard deviations above the mean. So lowest value of x. So we have this one, 500, and then 500 plus 2 times 40, because we're talking about 2 standard deviations above the mean. So the lowest value is 500 plus 2 times 40, which is 580. Right? Next, determine the highest value of x that lies at least 3 standard deviations below the mean. So we have 500 minus 3 times 40 is equal to 380. That is the highest value of x. The areas of certain regions under the normal curve represent the probabilities the value of the normal random variable x will lie within the indicated range of values. So for example, here, if you want to find the area below this normal curve from A to B, you just need to have probability of x between A and B. It is more convenient to compute the probabilities of normally distributed random variable x if the mean and the standard deviation are changed and fixed to mu is equal to 0. So the mean is 0. You will change the mean to 0 or convert the mean to 0, and standard deviation sigma to 1. So earlier we had 500. Instead of making 500, you need to convert that to 0 for easy computation. And then 40 standard deviation will be converted to 1 for easy computation as well. And as a result, we have this 0 for the mean, and then 1 standard deviation above the mean, 2 standard deviation above the mean, and so on and so forth. 1 standard deviation below the mean, 2 standard deviations below the mean, and so on and so forth. Thus, changing all the values of x to another random variable z, in which z is the small letter z is the value of z. This special random variable z is called the standard normal random variable. The value of z is called the z-score, or the standardized value of x. So earlier, x is equal to 500, and we changed that to z-score, which is 0. The probability distribution of the standard random variable is called the standard normal distribution. So here, because we changed already to z-scores, so this is already called standard normal distribution, or z distribution, and the graph is called standard normal curve. The random variable z, denoted by this symbol, has a probability distribution function of this equation, where z is equal to x minus mu over standard deviation. This is how you're going to change x values to z values. Okay, this formula is used to convert x to z-score. Using the previous example, mu is equal to 500 and standard deviation is 40. The z-value or z-score of 540 is, using the formula, 540 minus mu over 40, which is 1. And then, for 460, 460 minus 500 over 40 is negative 1. So that's how you change the value x to z. Construct a normal curve representing the graph of a normally distributed random variable x with mean mu is equal to 120 and standard deviation of sigma 15 and its corresponding standard normal curve. First, for the x-axis, for the values of the x-axis, we plot first the mean 120 and then we plot one standard deviation above and below the mean. So this is above 135 and then for the mean 105. 150 to 2 standard deviations above the mean and then 2 standard deviations below the mean 90. And then 165, 3 standard deviations above the mean and then 3 standard deviations below the mean is 75. So these are the x values. Now for the y values here, we'll be using this formula or equation. So for the x, we have this 75, 90 and so on. Converting that to z, so that is z, negative 3, negative 2, up to 3. And then for the y, we just need to substitute this 75, the x values, 90 and so on, to our equation. And we'll be getting this. Again, this exp is e or 2.72 raised to this expression. So after doing that, these are the values, 0.0025 and so on. And because this is symmetric about the mean, if this is 0.0025, this one is also 0.0025. This is 0.0035 and so on. This is 0.0035 as well, and so on and so forth. Now, as a result, we have the normal curve of this. So if x is 75, y is 0.0025. If x is 90, y is this. X is 120, so y is 0.026 and so on. Because that is symmetric, they're just the same. So this one is the same as this. This is the same as that and so on. So this is the normal curve. Now for the standard normal curve, we will be using the z-scores. We'll be changing the x values to 0, 1, 2, 3, and then negative 1, negative 2, negative 3. For the y values, they will be stayed the same. So this is the standard normal curve for z-scores. Now to differentiate the two, for the x values of the normal curve, we have the real values of x. And then turning that to z-scores, and then same graph, we have the standard normal curve. Again, this is normal distribution, this is z distribution. So that's the difference between the two.